All right, and now I want to go to this thing. All right. Next, I don't know. Autofocus. All right, I think the pencil will work. All right, so we're going to get into 2.2. So 2.2, and I'm sorry I'm left-handed. I kind of write over stuff, but anyway, I'll take care of this. But this is operations with functions. So again, we're going to get back into dealing with functions. So it's always going to be f of x and some expression of x, or g of x and some expression of x. And then we're going to be doing various operations with those. So this definitely builds on what we talked about in 2.1. So 2.2 will typically give you one of the four major operations involving functions. The notation looks like this. So first we've got the f plus g of x, or say the f minus g of x, or f times g. Sometimes they just write the f and the g right next to each other. Sometimes there's a little dot here, but that means multiplication, or f divided by g of x. And each of these implies, okay, evaluating the one function, evaluating the other, and then doing the operation in between. So again, addition means to add, or subtraction means to subtract. Or guess what? Multiplication would be to multiply. And division would be to divide. And they're going to ask you a number of different questions with these. They'll give you various functions, and some are very specific and some are very generic. And like I said, basically this is the notes. Like this is what we're doing within this specific lesson, but it's a lot of the algebra of how it all plays together. So that's why we're going to work through a bunch of examples so you can kind of see how things play, as well as some of the different questions they'll ask you and things they'll ask you to do. But this is the crux of what we're doing in 2.2. This is the basics of it. So one of the first examples, I give you some functions. We'll say f of x is x plus 3. We'll say g of x is x squared plus x plus 1. Okay, so again, they can give you 2, they can give you 3, they can give you multiple functions, and these functions will change. Like this is not always f of x, just like this is not always g of x. They can throw in an h of x. These functions will change. But then they might ask you something very specific. These are the easiest of the problems. If they give you a specific number to evaluate the function for, you're going to be plugging that specific number in, and you're going to get a pretty little number answer. So in this particular case, they want us to find the f plus g of 2. So again, this implies finding the f of 2 and finding the g of 2, and then adding those two values together. So to find the f of 2, that means to plug 2 in for the x of the f function. So if f of x is x plus 3, f of 2 means to take 2 plus 3, or 5. Okay. Similarly, the g of 2 implies plugging that 2 into the x of the g function. So since there's two x's, we're going to plug that 2 into both of those. So we're going to plug in 2 to the second power, plus 2, and plus 1. So again, evaluating the function is plugging in for the variable. Then we use order of operations. 2 to the second power is 4. This is just a 2. 1. 4 plus 2 is 6, plus 1 is 7. And again, the plus operation we're doing, so f plus g of 2 means to take these two values and then add them together. So this is going to be 12. So again, when you're evaluating it for a very specific number, you're going to get a very specific answer. The first couple of problems in your homework ask you a question very similar to this. It's going to be very specific. Okay, I'm going to do another example. Same functions. I just got to change papers here. But f of x is still x plus 3. V of x is still x squared plus x plus 1. And say I want to evaluate the f minus g of negative 1. Okay, and I did this on the last problem and didn't make a big deal about it, but when you start dealing with negatives, it's going to be important to include parentheses, because when you plug in something squared, a negative squared, the parentheses are going to matter, and I'll talk about that in just a second. But again, this problem implies, again, I want to find the f of negative 1, and then I want to find the g of negative 1, and I'm going to subtract those two values, one from the other. So again, f of negative 1 implies plugging negative 1 into the x of the f function. So negative 1 plus 3 is 2. G of negative 1 implies negative 1 into both x's of the g function. And again, this one in particular, the parentheses matter. If you punch that into your calculator, negative 1 in parentheses squared. Real quick, just kind of a side note. So negative 1 squared as opposed to negative 1 in parentheses squared. If you punch this into your calculator with no parentheses, it's going to tell you the answer is negative 1. Okay? In math, parentheses group things together. What your calculator sees, actually what this problem is specifically implying, is this is the negative of 1 times 1, which is why it's giving you a negative 1. And that's not what we're wanting in this case. In this case, we want to use our parentheses because, again, what we're actually implying, what we're actually wanting, what I want to see is, in this case, we're actually taking the value of negative 1 times itself. So when you group it in parentheses like we want, negative 1 times negative 1, that ends up equaling a positive 1. So we don't want the negative 1 counterpart. Make sure we're getting the right thing, especially if you use your calculator to figure this out. You're going to want to include the parentheses. That's going to matter. So negative 1 squared is 1 plus negative 1 plus 1. So 1 minus 1 is 0, plus 1, that value is 1. We got ones for days. And then remember, as the operation, we're going to be subtracting. So 2 minus 1, the answer to this one is 1. It doesn't matter really where you write it, that's just the answer. I tend to work down the page. Some people work horizontally. That's neither here nor there. That's just a personal preference. But that's how your homework is going to start. And they can give you multiple functions, but they're going to do it something specific where you're plugging a specific number in. You get specific number answers. Everything plays really, really nicely. Okay? Again, not the only operation, though. So again, just staying with the same functions. Then they'll get more generic. So they'll say something like, what is the f plus g of x. Now, anytime they're asking you to do this for an expression of x, x plus 1, x minus 1, 2x, something like that, once they start throwing variables in, you're going to get a variable answer. Okay, your answers are going to get ugly, is what I call it. Okay, you're not going to get like 1 or 4 or -2 typically. Okay, you're typically going to get some answer in terms of x. So again, what this implies is the f of x plus the g of x. F of x is exactly what it shows here. That's x plus 3. G of x is x squared plus x plus 1. And then I have to add those two things together. And this is where algebra comes into play. So when it comes to algebra, really math in general, if you are adding, you can only combine like terms. Like terms have the exact same variable to the exact same exponent. Okay, just like apples and oranges. You can't add apples and oranges together. If you've got 2 apples and 2 oranges, you've got 2 apples and 2 oranges. They don't combine if you have a smoothie maker. Okay, but anyway, you got to make them the same thing if you want to combine them. So in this particular case, the x squared doesn't combine with anything, so he's going to stay put. Okay. This x, if you don't see a number in front of it, it's an implied 1. There's 1x there. Okay, same thing here. There's 1x here. So if we combine this 1x with this 1x, we have 2 x's. We can combine this 3 with this 1. So 3 plus 1 is 4. So this is the f plus g of x. So again, the more generic they get, the uglier the answer gets. Now, also to go back to the previous lesson, 2.1, they may ask you, what is the domain of this particular function? If you remember, domain is almost always all real numbers. And we say it like this. This is interval notation. This says from -infinity to infinity. It covers every possible number. Most of the time, this is going to be your domain. And again, going back to 2.1, I'll talk about it, but a little more specifically, there are only 2 things that can limit your domain from this all real numbers. That's if you would have some kind of fraction or if you would have some kind of square root. These both have limiters. You can't have division by 0. You can't take square root of a negative number. So when we get into some examples where we could potentially limit our domain, I'll talk about those. But these are the only 2 things that will really limit what your domain could possibly be. So most of the time, your domain is going to look like this. And for these 2 particular functions, it doesn't really matter what we do with our functions. That's what our domain is going to look like. A polynomial function will typically have a domain of all real numbers. Okay. We're going to do the same f of x, g of x function. So we're still going to use x plus 3. And we're still going to use x squared plus x plus 1. But I want to do the f minus g of x, because this is one of those things that has something that if you're not paying attention, it can kind of get lost on you. It's got a very specific kind of trick to it. So again, this implies f of x minus g of x. So f of x is still x plus 3. g of x is still x squared plus x plus 1. Now, with subtraction, okay, on the whole number problem we did up here, okay, all you had to worry about was one number, so it didn't really matter. You can put your minus here in the middle, 2 minus 1, okay? When you have a polynomial, in other words, if you have multiple terms, okay, if you just put the subtraction here and you don't do anything else with it, this just looks like x plus 3 minus x squared plus x plus 1, okay? You have to remember you're really subtracting this whole quantity. So what that means is you've got to distribute this negative to everything. You've got to make sure you're subtracting each of these quantities from this x plus 3. So in this case, the x plus 3 is not going to change, but when we subtract the g of x, we're actually changing all of these to a negative. If one of them would have been negative, that would have changed to a positive, and I can show you an example of one of those, but in this case, these are all negative values. So when you're subtracting a quantity, make sure you distribute that negative to everything. So when we combine our like terms, we get a negative x squared. Here, our positive 1x and our negative 1x, those things actually cancel each other out. They equal 0. Positive 1x, negative 1x is 0. And then positive 3 plus negative 1 is a positive 2. So this would be the f minus g of x. And again, if they ask for the domain, it would be the same domain. The domain would be all real numbers. There's no limiter there. Okay, I'm going to do one more example with those same particular functions.
Can I ask a question?
Yes.
So on the last one, when we were distributing the negative to all the things behind the parentheses,
Yes.
And you canceled out the x in front of the 3.
Yes.
Why didn't we cancel out the 3? And if we did cancel out the 3, where did it go?
The positive 3, sorry, so the positive 3 and the negative 1, so 3 minus 1 is 2. That's where that came from.
Okay.
But the x and the 3 are separate. So this is 1x plus 3. So the 1x with this negative 1x, those are the things that canceled each other out.
Right.
So if I took this exact same problem, just write it in a different order. So I've got negative x squared plus 1x, okay, minus 1x plus 3 and minus 1. So basically, if I just took these in a different order, you can see how they group together a little better. So the negative x squared is there. 1x minus 1x, those two canceled each other out. And then the 3 minus 1 is what became the 2.
Yeah, I see how you got it now. I knew that you said you would cancel out the x, but then I didn't see that we had canceled out the 3, or didn't cancel out.
Got it. Good question. Okay, so again, last example I want to do with this particular function, then we'll switch it up. But we're going to change the order and the operation. So we're going to do the g divided by f of x. And it's just easier, like when we do the division, we're actually going to treat it kind of like a fraction. So in this case, we'll take the g of x over f of x. Now, a couple of things I want to point out here. This is one of those things. Come on, focus. There we are. This is where some people will tend to try to overmath this, or they just see stuff and it's like they vaguely remember in some math class where you got to cancel stuff out, and they see, oh, look, I've got an x on top and an x on the bottom, and I can just cancel those things out. Okay, that's bad math. All right, so I'm just going to do a side note over here. So if I show you 1 plus 3 divided by 3, okay? If I did bad math and canceled those 3's, I should just get 1 for my answer. But you know how math works. 1 plus 3 is 4, okay? And 4 over 3 is 1 1/3. It's not just 1. So again, you can't cancel those 3 out. You can't just break up an addition problem. So this does not simplify. This is our g divided by f of x. It doesn't get any simpler than this. This is our ugly answer. So there are times when it really is just as simple as writing the one over the other. Now, we do have a limiter within our domain. So our domain, if they ask, is no longer all real numbers, okay? Because we have a fraction, we might accidentally end up with division by 0. So we're not going to do that all real numbers anymore. Okay, remember, if we have a fraction, we got to figure out, are there any numbers that make this, the bottom, the top doesn't matter, but are there any numbers that make the bottom equal to 0? So if I set up x plus 3 equals 0, that's a plus. X plus 3 equals 0. And if I solve this for x, okay, -3 causes my bottom to be 0. And in math, you cannot divide by 0. You can't take something and divide it 0 times. That doesn't work. So -3 is bad. It causes division by 0, so we need to eliminate it. The way we showed that with interval notation is this right here. So basically, this is saying from -infinity to -3, and then from -3 to positive infinity. Because these aren't included, we're basically eliminating the -3. So when you have a fraction, that's one of those times where you have a domain limiter. And interval notation is how we say it. You can say it algebraically, but this is what they're looking for in terms of interval notation. Again, that's what my math lab and that's what this class is asking you to write your domain using. All right, I want to switch up the functions. We're going to do a little bit of the same. So f of x equals x squared. H of x is going to equal the square root of x plus 2. And we'll start out specific. So we'll take the f times h of 7. So again, specific, anytime they give you a number, they're asking you to plug that number in. So this is the f of 7 times h of 7. Plug our 7 into the f function, 7 squared, 49. H function, if we plug our 7 in, square root of 7 plus 2, the square root of 9 is 3. And then in this case specifically, they're wanting us to multiply 49 times 3, be 147. Okay, so again, specific number, very specific answer. They give us something generic, like say f times h of x. Again, this implies f of x times h of x. F of x is x squared. H of x is square root of x plus 2. And again, there's nothing you can really do with this. So again, square roots don't behave like parentheses, so you can't really distribute in. So this one, we would just leave like so. Again, if they ask for the domain, this one also has a limiter. So just like fractions are a limiter, so are potentially square roots of a negative number. The x squared doesn't matter. It doesn't matter what you plug in for x. You can square anything. You can square 1. You can square 17. You can square negative 3.9999999. Okay? Doesn't matter what you plug in here. Over here, the square root piece has to be positive. Okay? Square root of a negative number implies some kind of imaginary answer. We want to avoid that. So we have to figure out what kind of numbers can I plug in here that keep this from being negative. So we just take whatever's inside that x plus 2, and we need this to be greater than or equal to 0. It doesn't matter if it's 0. 0 is fine. The square root of 0 is 0. But it does have to be positive. We can't pick anything smaller than that. So if we go to solve, subtract 2, we need x to be greater than or equal to negative 2. So anything smaller than negative 2 is bad. Anything smaller than negative 2, if we plug it in, or sorry, anything smaller than negative 2 causes our value to be negative. So we want to use numbers bigger than negative 2. We use the bracket because it's equal to. Remember, the bracket includes the number. So negative 2 itself is fine. So if you're going to include it, that's why we used the bracket. Because we need this to be bigger than 0. If it's smaller than 0, that's going to cause this to be imaginary. So this is my domain limiter. This is my limiter. I can't have any negative numbers inside of the radical. So I need whatever's inside this x plus 2 to be 0 or bigger. I need it to be positive. Does that make sense? Okay, on a number line, okay, so you've got 0. Everything to the right of 0 is positive. Everything left of 0 is negative, anything less than 0. So we need our square root thing to be bigger than 0. So this is all good values. Anything that makes this x plus 2 bigger than 0 is a good value. So that's my domain. That's why I picked the greater than or equal to. And again, it can be equal to because 0 is fine. I just need it to go from 0 to the right. I can't have anything over here. And again, going back to the previous notes, that's my only 2 limiters within the domain. So if you get a fraction, anything that causes your fraction to be 0 is a limiter. If you have a square root, your square root, whatever's inside, needs to be greater than or equal to 0. That's how you find your domain. If anything that makes this equal 0, we need to eliminate. And we want to include numbers that make this bigger than 0. Otherwise, your domain is going to be that all real number. So fractions and square roots are basically your only limiters within your domain. Just kind of save space. I'm going to do 3 more examples with these functions, and then we'll transition to something else. All right, so we're going to find the f minus h of x. So again, that implies f of x minus h of x.
On the second one, are we doing f times f or are we doing f times h?
No, that's f times f.
Okay.
Yep. And then this one, so f of x minus h of x implies that we're going to take the f of x, and then we're simply going to subtract h of x. And again, we don't have any like terms to combine, so this one is what it is.
Will we have to find the domain of it too?
Yep. And if they ask you for the domain, really for all of these, if you look at the domains of your functions, there's not going to be a whole lot of things that's going to change it. We don't have any fractions. The only thing we're going to have is we can't let this be negative. And it's the exact same thing we did before. So we need that x plus 2 to be greater than or equal to 0. So we need our x to be greater than or equal to negative 2. So this same domain pretty much carries anytime we have h within our function. So this one, the domain, would be from negative 2 to infinity. I wrote that really small. Try a little bigger. That's not much better. Now, example number 2, they may try and throw you a curveball, so pay attention. Don't just fall into the habit. I have a tendency to put f first, just in terms of what I picked, but they could do h minus f. We did g divided by f. Also, they can double it up. So in this case, this is the f of x times the f of x. So again, this is implying taking this same function basically times itself. So this is saying x squared times x squared. Algebraically, if you're multiplying exponents of the same base, you can add your exponent, so that would be an x to the 4th power. If they ask for the domain of this one, h is not involved here. This is just f. Remember, this is just a polynomial function, so there is no limiter. So this domain can be everything. And then this last example is to take f of x divided by h of x. So that's going to be x squared over square root of x plus 2. Again, there's one little kind of tricky thing going on here with your domain. Okay, we need this to be 0 or bigger. We need this to be positive, but we actually can't use anything that would make it equal 0, right? So if I plug in negative 2 for my x, negative 2 plus 2 is 0, the square root is 0, but I can't divide by 0. So really the only difference when you have a radical on the bottom is instead of the bracket, I got to use the parentheses, because this can't actually equal 0. Anything just a little bit bigger than 0 is fine. It just can't actually equal 0. So I don't want to include the negative 2. Normally, I want to include it because 0 is fine. If this is on the bottom of the fraction, we can't include the negative 2. This is the bulk of what you're going to be doing. This is what most of the homework looks like. There are a couple of problems that they throw in here that I'm going to do my best to kind of try and work with. They give you some graphs. I'm going to keep it simple. That one's going to be my f function. That's going to be my g function. If they happen to give you two graphs, like so, and they're asking for, say, the f plus g of x, you kind of do this point by point. So this, okay, your x-axis, the horizontal, represents your input, meaning if I plug in the number 3, okay, this is the output for my f function. G doesn't have an output. If I plug in 2, this would be my output for the f function. This would be my output for the g function. Okay? So again, your domain is your inputs. The dots, the y values, represent your outputs. So f plus g of x is basically telling me to add the y values together. So if we look at this point, this is what? -2, -1. This is the point -2, +3. So if we were to add -1 and +3, that would be a +2. So again, you kind of do it point by point. So you're looking, really the x's don't matter. So while I did put the coordinates in, okay, at -2, I got a -1 y value here, a negative or a +3 y value here. We add 3 and -1, that gets me to 2. Okay, here at this one, okay, this one has a y value of 0. This one has a y value of 2. 2 plus 0 would be 2. See if I got it. Hoping this isn't too gross. Okay, if I do that in red, you can kind of see a little better. Okay. This one has a y value of +1. This one has a y value of 2. 1 plus 2 would be 3. This one has a y value of 0. This one has a y value of 2. 0 plus 2 is 2. This one has a y value of -1. This one has a y value of +3. 3 minus 1 is 2. And again, at that point, we run out of, the g function stops. So even though we have an f function here, it doesn't have anything to go with. So f plus g of x is represented by that red function. So again, you just kind of go point by point and you add the y values together. So specifically where the y's are, you would add those together. And that's what this represents. And the good news, on my math lab, these are all matching questions, so you're just going to match it up to the right graph. So this represents the f plus g of x. if they ask for the domain, that's basically asking, so what are your inputs? So the fact that we didn't have any more inputs out here and there's nothing over here, your graph only goes from here to here, and your domain is from -2, +2. All right, so I just kind of drew another example. And in this case, if they want us to find the f minus g of x, again, pay attention to order because it's going to matter which one is going to be the positive one, which one we're subtracting from. And again, we're just going to kind of do it. You do it point by point values, and you're looking at the y's. So again, specifically, this one has a y value of 0. This one has a y value of -3. So again, we're doing 0 minus -3, because again, the operation was subtraction. We're not adding this time, so in this case, we're subtracting. So when you subtract a negative, that's adding. That would actually be up here at +3. So again, we're taking the f minus the g function. So the f function was this one. So again, this is the one, so we're subtracting, so we're taking this one. The y value was 0. In this case, the y value was -3. So 0 minus -3. Okay, next one. So this one has, this is again the f function. This one has a y value of -1. G value has, or the g function has a y value of -2. So we're doing -1 minus -2. Again, subtracting a negative is adding. So -1 plus 2 is 1. And these next two end up being the same thing. So I've got a y value of 0 minus a y value of -2. 0 minus -2, 2. 0 minus a -2 is still going to be 2. So this red function represents the f minus g of x. So again, you just kind of do it item by item for each y value. And if we would flip-flop those around, that would change things, okay? And again, if they ask for the domain of this, we only have values from here to here. We never go left of 1, and we never go right of 4. So basically our domain would exist from 1 to 4. Specifically, the domain of F would go from -1 to 5. The domain of G is from 1 to 4. If we combine those, we only get values for where I can match them up. So it would only be for those. All right, we have one more thing to talk about within this section. That is called the difference quotient. The difference quotient is used primarily in calculus. It's a way to find a slope of a secant line. Okay. Anyway, there's lots of math that goes along with this. So somebody didn't just like make this up. I'm not doing this just kind of for fun. This actually is something, but it's primarily for later classes. Like if you get into calculus or some upper level math courses, they can have you figure this stuff out. So this is just an introduction to what the difference quotient is. And it's this particular combination, there we are, f of x plus h minus f of x all over h. So for any function f of x, we can find this difference quotient. So I'm going to give you a couple examples. One's a simple linear function, which is going to play really nice. The next one's going to be a polynomial function, plays a little less nice. But I'll show you some examples of these, and this will finish up 2.2. So if we had a nice little linear function, like say f of x equals 3x plus 1, and they want us to find this difference quotient. Again, the difference quotient basically has 3 parts. You've got this f of x plus h, that's a part, minus f of x, and then all over h. So if they want us to find the difference quotient, the first thing we're going to do is we're going to take this x plus h and plug it in for x. So this part looks like that. So this is the f of x plus h. Again, what they're asking us to do is take x plus h and plug it in for x. Then we're going to subtract f of x and that's all going to be over h. And then we're going to simplify this. We got some things we can do here, but so this is that first part. This is the f of x plus h minus f of x all over h.
So why does the 3 go on the outside of the parentheses?
Because we've got 3 times whatever the heck x is. So this function is saying whatever I plug in here for x goes here. And this is going to be 3 times that whole thing. So if it was just one number, it would be 3 times that number. Or if it was just an x, it's just 3 times that x. The fact that I'm plugging in 2 things, this x plus h, I've got to take 3 times both of those. So I've got to distribute that 3 to the x and the h. So if we distribute this out, we're going to get 3x plus 3h plus 1. And remember, I talked about subtracting a quantity. You got to just subtract both of these. So this is going to be minus 3x and then minus 1. And that's all going to be over h. Now, when we get to this ugly thing, we want to look and see if there's anything we can combine. Again, we can combine our like terms. So are there any like terms with the 3x? Are there any other x's? Yeah. Okay, we got this negative 3x. Okay, so positive 3x and negative 3x, those actually will cancel each other out. 3x's, take away 3x's is 0. So those are going to cancel each other out. Okay, same game. Can I combine anything with the positive 1?
The negative 1?
Negative 1. And in the same vein, positive 1 and negative 1, 1 minus 1 is also 0. So those cancel out. So then we're left with 3h divided by h. Now before, when we were dealing with pluses, we couldn't break anything up. But if we're multiplying 3 times h and divided by h, h over h is a form of 1. So those cancel out, leaving us with just 3. So this would be our difference quotient. Once we worked this whole thing out, everything canceled out all the way down to 3. That was clear as mud. We're going to do a couple more examples.
Is this the formula we'll need to remember for the test, or will it be on the test?
This will be on the test. I'll tell you this.
Okay.
All right, so this is the function. And just this is the formula, the difference quotient. So again, f of x plus h minus f of x all over h. So again, we got 3 different parts. We've got this part, and this part. So again, this first part, so this f of x plus h means I'm going to take this x plus h and I'm going to plug it in for x. So this is going to be x plus h, quantity squared, and then minus 1. That's this piece right here. Okay, then we're going to subtract f of x Again, I always put that in parentheses because when you're subtracting a quantity, we need to make sure we're subtracting both of those values. And again, that's all going to be over h.
All right, I have a question.
Okay.
The first parentheses that we're distributing, and you put the exponent of 2 over the parentheses. Why is it not 2x? Is it because x with an exponent of 2 is not the same as x?
Correct. So the little 2, so that's an exponent. So x to the second power and 2x do not imply the same thing. This is doubling it. So 2 times 3 is 6. But this is saying 3 times itself 2 times. Okay? So like if we plug in 3 squared compared to 2 times 3, right? 3 squared is 9, 2 times 3 is 6. Those aren't the same thing. So the little 2 is squaring something as opposed to, say, doubling it or whatever. So what this x squared means to take, again, whatever's here in the x, and we're going to square it.
So basically, x isn't an actual number in that situation. It's just like a placeholder for the x line?
Yeah. Okay, so yeah, in a function, it's almost always a placeholder. It's a variable that's representing whatever I want to plug in. Yeah, it's a placeholder.
So you want it combined like terms with the x plus 8?
Eventually.
Okay.
The trick is this x plus h squared, this piece right here.
Mm-hmm.
Again, we got to do some algebra with this. So I'm going to step over here to the side just so I don't kind of clutter up my problem here. But that x plus h squared means to take x plus h times itself. So anytime you're squaring something, you're taking it times itself. When we do this, some people call it, like I teach high school math, so some people say FOIL. It's a way of saying distribution. So you multiply those first terms. So x times x is x squared. We multiply the outside, so x times h is xh. We got to multiply those inside terms. So that's also xh. Multiply those last terms. So that's h squared. Since we have 2 of those. So just this piece here, that x plus h quantity squared, whenever you square 2 terms like this, we got to do this thing right here. So you take it times itself, and then you got to distribute or FOIL. So again, you multiply those first terms, those outside terms, the inside ones, and then the last one. So again, x times x is where that x squared came from. X times h, x times h, and h times h. And again, the only like terms are these 2 xh's. That's that. So again, that's just this piece. So x plus h quantity squared is x squared plus 2xh plus h squared. Okay. And then we have this minus 1. And then if we distribute our negative, we get a negative x squared. And then the negative of a negative makes that a positive 1. That's all over 8. Now, once we do that, now we can start looking for our like terms. So here, positive x squared and negative x squared cancel each other out. Same, negative 1, positive 1, cancel each other out. I can't combine those. Those are different. So I've got 2xh plus h squared over h. And again, we couldn't do this before because we had extra stuff, but when you get down to this point, if everything has an h, we can divide those h's out. So for example, this h and this h divide out to be 1. So that's going to leave me with just 2x. And then this h squared and this h, one of those cancels out. So then that's what we end up with. That's
So anytime we're doing these kind of problems and we end up with the same letter, we and cancel them out?
Correct. And the way these play out, the fact that like the way the difference quotient sets up where there's an H on the bottom, the fact that we're putting an H in, like parts of the f of x's are going to cancel out, like the x squareds and that -1. So basically anything not involving the H will probably end up canceling out. Just like here, the 3x's and the 1. Oops, the first problem I showed you. So again, the 3x's and the 1 again canceled out. So something with the H left over was what was left over. So by definition of how this works out, parts of this one are going to cancel out with this one, to where what I'm left with should all have H's, and then we can divide one of those H's out. So by definition, like lots of things are going to cancel out. We'll do one more example like that, and that'll finish up 2-2. 2-3 will go faster. 2-2 is bigger. The last example. All right, so again, here's my function. And again, this f of x plus h means to plug that x plus h in for both x's. So that part is going to look like this. So again, that's just this f of x plus h part. And then we're going to subtract f of x that's all going to be over h. Okay, and again, we did that x plus h squared before. So instead of walking through it again, I'm just going to grab this. Come on, focus. Okay, so that x plus h squared, this piece becomes that. So we get 2 x squared plus 2xh plus h squared. And then I'm just going to bring all this other stuff down. So again, this piece, this x plus h squared, became that again. And then I'm going to do all of my distribution basically in one step. So anything outside of the parentheses multiplies to everything inside. So we're going to get 2x squared plus 4xh plus 2h squared. We distribute this 2. We're going to get a plus 2x and a plus 2h. We distribute our negative, we get a negative 2x squared and a negative 2x. And again, we get this horrible, horrific thing, but you're going to see stuff kind of neatly and quietly cancel out and go away. For example, this positive 2x squared and this negative 2x squared. Anytime you have a positive and a negative of the same thing, they cancel out. Got this positive 2x and this negative 2x. We've got 4xh plus 2h squared plus 2h all over h. So again, as long as these all have an h, we can basically divide that guy out. So h divided by h is gone, so that's just a 4x. This 2h squared, the fact that we had an h squared, only one of those goes away. So that's going to leave me with a 2h. And then this h and this h cancel each other out. That's going to leave me with 2. So that is the different quotient.
You don't find domains to each book, right?
Say that again, I didn't hear you.
You don't find domains to these?
No. Nope. When we have two variables, like you have an x and an h, there's not really a domain for this. So no, this is not a domain thing. They're just, you're finding a specific difference quotient. That's all we're messing with this. And again, the bulk of the lesson, the important thing is what we were doing at the beginning with that whole f of x plus 1 or f minus g of x, stuff like that. There's just a couple of problems where they throw in the difference quotient. And if you go on and take some upper level math classes, this will be more important, but really this is just kind of a little blip within this unit. It's definitely not the focus of it. All right, with that, we're going to transition into 2-3. And again, this is all we're going to cover tonight. We'll do 2-4 and 2-5 next time. 2-3 deals with the composition of functions. The notation for this kind of looks like fog, especially if you write it in pencil. This is a circle. It's usually a slightly different font. You'll recognize it when you get into the My Math Lab. You'll see that it's slightly different. It doesn't actually look like fog. It's like F circle G of X. Okay, the way this is read is as the composition F of G of X. Another notation or another way to write this is like so. This is an embedded notation. And different than multiplication, which is what this kind of gets confused for, we basically work this from the inside out. So again, whatever we have here, we're plugging into the G function, solve that, then whatever full answer we get, we plug that into our F function. So again, looking at your parentheses, we work this from the inside out. And just like last unit, they're going to start specific and then they're going to get generic. So just two random functions. So say f of x equals 2x plus 1. G of x equals 3x. They could ask us to find the f of g of 2. And again, what this implies is the embedded function. So essentially, we're going to plug 2 into that g function. We want to find the g of 2. So if we plug 2 into the g function, we're plugging it in here. That's telling me to multiply 3 times 2. And again, what makes this one nice is when they're very specific, you get a nice, pretty little number answer. So 3 times 2 is 6. So then that answer, the 6, is what we plug into the f function. So we're finding the f of 6. So the g of 2 is 6. So then we're going to plug that 6 into our f function. So 2 times 6 is 12. 12 plus 1 would be 13. So the f of g of 2 is 13. So again, we plugged 2 into the g function. 3 times 2 is 6. We plugged 6 into the f function. So 2 times 6 is 12. Plus 1 is where we got 13. So as long as they're being specific, this is easier to kind of track. You're just plugging in your number, get an answer, plug that answer in, get the final answer. Okay, I'm going to use those same functions. I'm just going to rewrite them here. So f of x equals 2x plus 1. G of x is still 3x. But we're going to switch it up and say we want to find the g of f of negative 4. So again, they flip-flop the order here. So again, we're still going to work it from the inside out. This implies finding the g of f of negative 4. I'm going to plug negative 4 into the f function. So that's 2 times negative 4 plus 1. Come on. So 2 times negative 4 is negative 8. Negative 8 plus 1 is negative 7. And then I'm going to plug that answer into the g function. So g is 3 times whatever. So negative 7 is my answer. That's what I'm going to plug in. So 3 times negative 7 is that negative 21. So the g of f of negative 4 is negative 21. So again, as long as they're specific, anytime they give you a number to plug in, you're going to end up with a specific number answer. Where the answers get uglier is when they leave it in terms of variables instead of giving us a specific number, and then letters get involved and it's all kinds of fun. So same functions. F of x is 2x plus 1. G of x is 3x. We want to find the composition, f of g of x. Again, what this implies is f of g of x. I plug x into the g function, g of x is 3x. I can't do anything else with that. That doesn't simplify. It is what it is. So then I've got to plug this whole thing into the f function. Again, the f function says to take 2 times whatever plus 1. This is my whatever. So I got to take 2 times that 3x and then plus 1. I've basically plugged the g of x function into the f function. So this 3x goes into the f function. So 2 times 3x, 6x. So that would be 6x plus 1. Now again, when they get generic, sometimes they ask for the domain. If they ask you for the domain and there's no limiters, it'll be your all real numbers. And remember, your limiters are if there's a fraction or a square root. Division by 0 is bad. Square roots of negatives are bad. As long as they keep the function simple, everything stays pretty simple. The problem is they rarely keep things simple. All right. F of x equals x squared plus 2x. G of x equals 2x plus 3. And if they want us to find the f of g of x,
Will these always be multiplication?
I'm sorry?
Will these always be multiplication?
It's not multiplication, it's embedding. You're always plugging one into the other. So yeah, it's always that. So don't confuse this with multiplication. That's a circle. And again, what that means is you're going to take this whole function g of x and plug it into f of x. So yeah, it's not multiplication, but there's also no addition, subtraction. That was last unit. So this one, you're going to be plugging this whole thing into this one. Basically, again, you're embedding the function. You're putting it into the other one.
Okay, thank you.
Yeah. Yeah, so with this one, g of x is that 2x plus 3. So we've got to plug that into our f function. We're going to take 2x plus 3 and to square it. And we're also going to take 2 times that 2x plus 3. So f of x tells me to plug in for both of those. So I'm basically plugging my g of x function into both of those.
You pretty much know write it out right.
Correct. And unfortunately, this is where, again, algebra kicks in. We got to simplify this. We got to see if we can find some like terms to put together. So this 2x plus 3 squared means to take it times itself, which means we got to distribute. So 2x times 2x is 4x squared. 2x times 3 is 6x. 3 times 2x is 6x. And 3 times 3 is 9. Again, that's just this piece. Then we also have this 2 to distribute. So 2 times 2x is 4x, and 2 times 3 is 6. So algebraically, this 2x plus 3, quantity squared, became that piece. And this 2 times 2x plus 3 became that piece. Then I want to see if I can put anything together. So x squared, there aren't any other x squared terms. So he doesn't combine with anything. This 6x, and this 4x, we can actually combine all of those. So positive 6 and positive 6 is 12, and positive 4 is 16. And then the positive 9 and the positive 6, I can also combine. 9 plus 6 is 50. So this is my f of g of x. Again, with no limiters, if they ask for the domain, this would be an all real numbers situation. It's all one thing. So the question was, with the 2 times 2x plus 3, why did I bring that down with it? So again, it's all one big thing. So the g of x was just this one piece, and I had to plug it into f of x, which gave me 2 kind of parts. You see, I had to plug it in for both of those. So this is the whole thing. It's just not simplified yet. So this 2x plus 3 squared became that piece. And again, the 2 times 2x plus 3 became that piece, and I had to see if there was anything I could put together. And then after it's all put together, basically that's kind of the best way to write it. Does that make sense? If you want to stick around, I can show you another example after. Just we're getting close enough to time. I'm going to do one more example because there's one more problem they throw in the homework that's got a nasty little trick to it. I'm going to do one more. All right, so the initial functions are 2 over 1 plus x and 1 over x. And we're going to do this one both ways. We're going to find the f of g of x, and then we're going to do the g of f of x. To me, this one's the trickier one, but I'll show you. So again, if we want to find the f of g of x, we're basically going to take this g of x function, and we're going to plug it into the f function. So again, g of x is that 1 over x. And we're going to put that in place of the x here of the f function. So what we're going to get is 2 over 1 plus 1 over x. Now again, like I said, I teach high school math, so I joke around that math has math cuss words. those words you all learned to hate as like kids, so like word problems, that's a math cuss word. Another one is fractions. Fractions are like the biggest math cuss word there is. So whenever you have a fraction inside of a fraction, I call this a mother fraction. So we're dealing with a mother fraction here, so we got to get rid of this. So the trick to dealing with a fraction within a fraction, all right? We're going to multiply. So just kind of follow me. I won't walk through the whole explanation, but basically this is how we get rid of it. This denominator is what's causing all the problems. This x down here. To get rid of him, we're going to multiply. So we're going to take this whole bottom times x. But we can only do that if we multiply the same thing to the top. We got to multiply by a form of 1, which seems gross, but it's actually going to make everything play really nicely together. So again, the reason we can do this is because anytime you divide something by itself, it's a version of 1. So we're not changing our number. We're multiplying it by a form of 1. So if you can follow me here, x times 2 is going to be 2x. X times 1 is going to be 1x. And then x times 1 over x is just 1. So then that makes it where it's not a mother fraction anymore. It's just a regular fraction. So it's kind of like a nice cuss word instead of a bad cuss word.
For these, do we cancel out?
Say that again?
Do we cancel out these ones?
Yeah, no, these do not because of the plus sign. So before we could cancel out all those h's. If I go back to my notes, okay? Because they all had the h's, we were able to do it. The fact that like there's no x here, right? So we can't divide that x out of everything. So yeah, don't try to overmath this. This is actually as simplified as this one gets. Now, the domain for this one is tricky. Because x was on the bottom here, and because we multiplied it by x over x, looking at this problem, we still can't allow x to be 0. Even though it doesn't matter here in our finished problem here, within the context, if x is 0, that causes division by 0. So we still have to eliminate this guy. And then same, once we get to here, x plus 1, we can't let that equal 0 either. So we have to eliminate -1 as well. And actually, if you look at our original functions, that's our two limiters anyway. We can't let x be 0, and we couldn't let x be -1. 1 plus -1 causes this to be 0. So these have to both be eliminated. So my domain is going to look like that. And I'm going to rewrite that where it is all on one line and looks better. Okay, so this is how we would say that. Again, if we want to eliminate a number, this is kind of the process for it. So it's from -infinity to the number we want to eliminate, parentheses in conjunction with, from that one. And then it just has to read from small to big. So because -1 is smaller than 0, that's why we did it first. And then we did the 0 next. So again, this is kind of the mechanics for eliminating a number. Okay. Similar problem, just working in the other way around. So in this case, we're finding the g of f of x. That f of x is 2 over 1 plus x. And then if we plug that into the g function, then we're going to get 1 over 2 over 1 plus x. Again, we can't leave looking like this because we got another fraction. We got fractions in fractions. That's no bueno. So again, we're going to multiply by our denominator. We got to multiply the same thing, top and bottom, so that 1 plus x. That's a 1 plus x. Didn't realize, man, must be getting tired. My handwriting has gone to absolute crap. It's normally bad, but this is like extra bad. All right, so anyway, if we multiply 1 plus x times 1, that's just 1 plus x. And if we multiply our 1 plus x times 2 over x plus 1, basically those two things cancel out, leaving me with just the 2. As far as our domain goes, again, from the original problem dealing with the 2 and the 1 plus x, we do still have to eliminate the negative 1 because that would cause division by 0. And then we do still have to eliminate, no, in this case, we don't have to worry about that. Okay, so as long as we eliminate the negative 1, that's the only one we have to eliminate. Because the fact that we're plugging the f function into the g function, we're covered there. The 0 doesn't affect us because we're always going to have a function here. So the only number we have to eliminate is the one that causes this f of x to be bad. That's the negative 1. And that's all we got for 2.3. So if you have a question, you can stick around and ask it. If you would like to be done, your brain is fried, you've had enough mother fractions for the day, you can call it good. Again, I would recommend the couple of you that haven't logged into my math lab, please do so, and make sure you're catching up on your homework. So right now we've got 4 assignments worth of stuff that I've covered. The sooner you can get that done, the more you can stay on top of things, the better. You get behind and it just turns into this giant pile of stuff you don't want to do. So anyway, that's my advice. If you have a question, you can ask it. Otherwise, you're free to go, and I'll see you next Thursday.
I have a question.
I have an answer.
Where did you get the negative 1 at? Did you just take it from the top equation since it's just a flip-flop version of it?
Right. So the negative 1, if I plug negative 1 in here, that's what's going to cause that division by 0. So I was just looking at that.
Oh, okay.
Okay?
Yeah, I got that.
Got it. Good.
I don't know how you do attendance, but I came in late, so I don't know if like you had already done attendance.
What's your name?
Tiffany?
Tiffany, how do you say your last name?
Kershoni?
Got it. Okay, yep. Perfect. Thank you.
Thank you. What did you say?
I said, you're the other Tiffany.
Oh, your name is Tiffany.
Yeah.
That's why you asked my last name. I was like,
I already got you. I got you coming in. Well enough, you're good. All right. Bye, guys.